Good day, everyone. We are Group 4 from Bsece 44, and we are presenting renewable energy, solar energy application. And I am Joshua Miguel Mana with my team, RJ Ordinario and Alan Aldrich Comsty. For our introduction, since solar energy is both free and non-polluting, has been an extensive study into developing solar technology for decades. The sun is a magnificent renewable resource that has a capacity to support life on Earth by providing clean, renewable energy to all of its inhabitants. In fact, the sun sends more energy to our planet in an hour than the entire world's population uses in a year. Solar photovoltaic or PV modules turn the sun's energy into electricity. Photo means light and voltaic means electricity. Solar energy has the greatest potential of any energy sources, and there is no limit to how much of it may be used to meet our energy needs. The conversion of solar energy into other useful forms of energy can be accomplished by the three conversion processes. One is the heliochemical process, the second one is the heliothermal process, and last but not the least is the helioelectrical process. The heliochemical process, this is basically photosynthesis process and it is responsible for the production of fossil fuel and biomass. The heliothermal processes, solar energy is collected and converted to thermal energy or heat. Flatlet collectors, concentrating collectors, and heliostats are commonly devices that collect solar radiation for conversion to useful heat. Last is the helioelectrical process. The production of electricity by photovoltaic or solar cell is accomplished by a helioelectrical process. This process is different from the heliostats in that solar energy is converted to electricity directly in solar cells, while it is first converted to thermal energy in heliostats. Solar engineering process. The two main categories is the active application, which include practically all solar collector, solar cell, and heliostats application, entails some mechanical, electrical action, and device such as pump system. Electrical and mechanical equipment are used in active solar energy. Passive solar energy, on the other hand, is solar energy that does not require any other energy or mechanical system. It is the use of direct and live sunlight to generate power or heat. The next one is the passive solar application is any application that tries to use solar energy through a passive architecture of a system. Passive solar heating system captures sunlight within the building's materials and then release that heat during periods when the sun is absent, such as at night. South-facing glass and thermal mass to absorb, store, and distribute heat are necessary in the design. A solar collector A solar collector goal is to convert sun energy into a usable heat. The majority of solar collectors in use today are used to generate hot water. The hot water is typically used in kitchen, restroom, showers in both residential and commercial establishments. In the winter, solar collector can be utilized for room heating. A solar collector is an item that collects solar energy by absorbing it and converting it to heat or electricity. A solar collector material and coating are chosen to enhance solar energy absorption. Next are the flat plate solar collector, glazing, an absorber plate, a flow tube, insulation, a glazing frame, and a box enclosure make up a flat plate collector. Solar radiation is absorbed by the absorber plate as it passes through the glazing, which is a form of glass. The absorber plate is connected to flow tubes. The water is heated as it passes through the tube by absorbing heat from the absorber plate. To reduce heat loss, the side and the rear are insulated. The image shows the flat plate solar collector. So the formula for the rate of solar heat absorbed by the subsorber plate is Q abs is equal to tau alpha Ag, where the T is the transmittivity of the glazing, A is the absorptivity of the absorber plate, A is the area of the collector surface in meters squared, and G is the solar insolation or irradiation, solar radiation incident per unit surface area in W over meter squared. The rate of heat loss can be expressed as Q loss is equal to UA is times Tc minus Ta, where U is the overall heat transfer coefficient in W over meter squared times degree centigrade that accounts for combined effects of convection and radiation. Tc is the average collector temperature and Ta is the ambient air temperature, both in degrees centigrade. The useful heat transfer to the water is the difference between the heat absorbed and the heat loss, which Q useful is equal to Q abs minus Q loss. These are the graph which, which shows the collector efficiency for the three different collectors, which shows that the no glazing is the highest efficiency. The specification of two plate collectors are given as follows. Single glazing is T is equal to 0.96, A is equal to 0.96, U is equal to 9, W is over meter squared times degree centigrade. The second one is the double glazing, which T is equal to 0.93, A is 0.93, U is equal to 6.5, W over meter squared times degree centigrade. The concentrating solar collector. The concentration of solar energy is low, and as a result, the temperature of hot water obtainable in a flat plate collector is low, usually under 80 degrees centigrade. Hot fluid, water, steam, air, or another fluid at much higher temperatures can be produced using concentrating collectors by concentrating solar radiation on a smaller area. This is the this is the image for concentrating solar collector. The most common type of concentrating solar collector is parabolic through collector, which has a receiver, outlet, inlet, and a parabolic concentrator. This is the concentrating solar collector. In a concentrating collector, solar radiation is incident on the collector surface called aperture area, which is A sub A, and this radiation reflected or redirected into a smaller receiver area A sub R. The concentration factor is defined as CR is equal to AA over AR. This the image shows the solar concentrator power plant using parabolic through collectors, which sun directly to the parabolic tube, which is a receiver, then has a steam condenser, thermal storage tank, which goes to the generator or turbine that produce electricity.
Next is the solar power tower plant. A solar tower power plant uses a large array of mirrors called heliostats that track the sun and reflect solar radiation into a receiver mounted on top of a tower. Electricity can be produced from solar energy by direct conversion of solar radiation into electricity or by using parabolic draw collectors. Water is heated, boiled, and superheated by absorbing heat from the receiver system. The resulting steam is then directed to a turbine to produce power. A generator is connected to a turbine to convert turbine shaft power into electricity. As you can see on the picture is an example of a solar power tower plant. The first large-scale solar power tower plant is Solar One, located in Barstow, California. It has a capacity of 10 megawatts. The tower is 91 meter high or 300 feet and at the top of the receiver and at the receiver located at the top of the tower is water cooled. There is an oil sand storage unit that can help supply electricity for 3 to 4 hours after sunset. The total cost of Solar One plant is $14,000 per kilowatt, which is 5 to 10 times greater than the cost of electric power stations that run on fossil fuel and other renewables. Next is the German solar power plant located in Seville, Spain consists of 2,650 heliostats that focus 95% of solar radiation onto a giant receiver. The plant started commercial operation in 2011, occupying a field of 185 hectares. The temperature, as high as 900 degrees Celsius, are obtained at the receiver. Molten salt tanks are heated by concentrated solar heat reaching a temperatures above 500 degrees Celsius. Water runs through the molten salt tanks in which it is boiled and superheated. The resulting steam is directed into turbines to produce power. Steam leaving the turbine is condensed and pumped back to the molten salt tanks to repeat the heat engine cycle. Next is Ivanpah Solar Power Plant started commercial operations in 2013 after a 3-year construction period. It consists of three separate units. The electricity generated can serve 140,000 homes during the peak hours of the day. The plant is located in Mojave Desert, which is in California, and it is the largest solar thermal power plant in the world with a capacity of 377 megawatts. It is located at an area of 3,500 acres or 14.2 square kilometers with 300,000 concentrated mirrors reflecting solar energy to receivers at top of the three towers in three plants. The towers are 140-meter high. Germa Solar Park, Germa Solar Plant in Spain, Solano Plant in Arizona, and Crescent Dunes Solar Project in Nevada all use energy storage in using molten salts. This ensures power generation during evening peak hours. Solana and Crescent Dunes plant can produce power up to 6 and 10 hours of storage after sunset, respectively. Ivanpah, on the other hand, it does not include any energy storage system. Next is solar pan. It is a method of power generation that involves collecting and storing energy in large artificial lakes a few meters deep. The main disadvantage, though, of a solar power plant is its low thermal efficiency. Next is the image of the operation of a solar plant. So solar energy is absorbed by all parts of the pond, and the water temperature rises everywhere. The top part of the pond, however, loses to the atmosphere much of it absorbs, and as a result, its temperature drops. This cool water serves as insulation for the bottom part of the pond and helps trap the energy there. Uh, this usually salt is planted at the bottom of the pond to prevent the rise of this hot water to the top. A power plant that uses an organic fluid such as alcohol as the working fluid can be operated between the top and bottom portions of the pond. Next is thermal efficiency. So solar pond, the the operation of the solar pond works as the principle of entropy. So from this we can determine the maximum thermal efficiency by maximum thermal efficiency is equal to 1 minus the temperature near the surface of the pond over the temperature near the bottom of the pond in kelvins. So for example, if the water temperature is 35 degrees near the surface of the pond and 75 degrees at the bottom, so the maximum thermal efficiency can be determined to be maximum thermal efficiency is equal to 1 minus 35 converted to kelvins over 75 converted to kelvins also is times 100, which is equal to 11.5%. So actual thermal efficiency will be less than this value. Next is photovoltaic cell. A photovoltaic system consists of an array of solar cells which converts electromagnetic radiation into electricity. It is a non-mechanical device that converts sunlight directly into electricity. Some photovoltaic cells can convert artificial light into electricity too. So photovoltaic cell. Photovoltaic cell Photovoltaic system converts electromagnetic radiation into electricity. The cell involves a p-type semiconductor and an n-type semiconductor. Silicon is commonly used as a semiconductor material in solar cells. The silicon is doped with phosphorus to produce an n-type semiconductor, and while it is doped with boron to produce a p-type semiconductor. There is a current density flow at the p-n junction of a solar cell. So solar radiation incident on a solar cell is originated from the sun. The upper limit of the thermal efficiency of a cell may be determined from the Carnot efficiency by using the effective surface temperature of the sun, which is 5780 kelvins, and an ambient temperature of 298 kelvins. So next is however, due to various reasons, the theoretical efficiency limit is considered to be about 34% for a single junction solar cell. This can be exceeded by multiple junction solar cells. If an infinite number of junction is used with high concentration of solar radiation, the limit then becomes 86%. So silicon has been commonly used in solar cells, but the commercial silicon solar cells have a low efficiency, only about between 15 and 20%. Other materials have been tested extensively in order to increase solar cell efficiencies. They include silicon, cadmium telluride, cadmium sulfide, copper indium diselenide, gallium arsenide, gallium phosphide, and indium phosphide. Copper indium diselenide and gallium arsenide are among the most promising material. Next is a single solar cell produces only 1 to 2 watts of power. Multiple cells should be connected to form modules, and modules should be connected into arrays so that reasonable amounts of power can be generated. This way, both small and large photovoltaic cell systems can be installed depending on the demand. Lastly, the lifespan of a solar cell is about 20 to 35 years. So, collection of dust on panel surfaces over time reduces the performance of solar panels.
The solar power capacity has increased by 97 gigawatts in 2017, by 53 gigawatts in China, and 11 gigawatts in the United States, bringing the world total to 400 gigawatts. The capacity nearly quadrupled in the last 5 years. The a steady increase in solar power installations is expected in the coming years. Main reasons for this expected trend are as follows. First, cost of solar panels has been declining. Second, there is a growing market in Asia, particularly in China, India, and Japan, especially after Fukushima nuclear disaster. Third, cost of financing solar projects is likely to be declined. Fourth, public interest and awareness in renewable and particularly in solar energy is growing. Fifth, conversion efficiencies are getting higher due to extensive research and development. And lastly, there are growth and improvements in complementary technologies to solar power such as storage and smart grid. Passive solar applications. The use of solar collectors for water and space heating and electricity production and photovoltaic cells for electricity generation represents active solar energy applications. The use of energy by means of engineering design without the involvement of mechanical equipment is called passive use of solar energy. Significant energy savings can be accomplished if a house is designed and built to receive maximum solar heat in winter to minimize heating energy consumption and minimum solar heat gain in summer to minimize cooling energy consumption. This may include correct selection of orientation of walls and windows, size and type of windows, wall materials, and surface color and finishing of wall surfaces. Of course, particular preferences in design and construction of buildings will be different in winter-dominated and summer-dominated climates. The solar heating of swimming pools, food drying, and solar cookers are some other examples of passive solar applications. Trombol. These dark painted thick masonry walls called trombols are commonly used on south sides of passive solar homes to absorb solar energy, store it during the day, and release it to the house during the night. The idea was proposed by E. L. Morse of Massachusetts in 1881 and is named after Professor Felix Trombe of France, who is extensively in his design in the 1970s. Usually, a single or double layer of glazing is placed outside the wall and transmits most of the solar energy while blocking heat loss from the exposed surface of the wall to the outside. Also, air vents are commonly installed at the bottom and top of the trombols so that the house air enters the parallel flow channel between the trombol and the glazing, rises as it is heated and enters the room through the top vent. Solar heat gain through windows. The part of solar radiation that reaches the Earth's surface without being scattered or absorbed is the direct radiation. Solar radiation that is scattered or re-emitted by the constituents of the atmosphere is the diffuse radiation. Direct radiation comes directly from the sun following a straight path, whereas diffuse radiation comes from all directions in the sky. In the left figure, this is the direct, diffuse, and reflected components of solar radiation incident on a window. The radiation reaching a surface in general consists consists of three components: direct radiation, diffuse radiation, and radiation reflected onto the surface from surrounding surfaces. Common surfaces such as grass, trees, rocks, and concrete reflect about 20% of the radiation while absorbing the rest. Snow-covered surfaces, however, reflect 70% of the incident radiation. Radiation incident on a surface does not have a direct view of the sun, consists of diffuse and reflected radiation. On the right side, this is the distribution of solar radiation incident on a clear glass. When solar radiation strikes a glass surface, part of it, about 8% for uncoated clear glass, is reflected back outdoors. Part of it, 5 to 50%, depending on composition and thickness, is absorbed within the glass. The remainder is transmitted indoors. The standard 3 mm thick, 1/8 inches, single pane, double strength, clear window glass transmits about 86% and reflects 8% and absorbs 6% of the solar energy incident on it. This is the table shading coefficient Sc for and solar transmittivity solar for some common glass types for summer designs conditions. This is the type of glazings and its thickness. For the single glazing, clear, 3 mm, 1/8 inches, T solar, 1.0 SC, 6 mm, 1/4 inches, 0.78 T solar, 0.95 SC, 10 mm, 3/8 inches, 0.72 T solar, 0.92 SC, 3 mm, 13 mm, 1/2 inches, 0.67 T solar, 0.88 SC. For the heat absorbing glass, 3 mm, 1/8 inches, 0.64 T solar, 0.85 SC. 6 mm, 1/4 inches, 0.46 T solar, 0.73 SC. 10 mm, 3/8 inches, 0.33 T solar, 0.64 SC. 13 mm, 1/2 inches, 0.24 T solar, 0.58 SC. For the double glazing, clear in, 3 mm, 1/8 inches, 0.71 T solar and above, 0.88 SC. For the clear out, 6 mm, 1/4 inches, 0.61 T solar, 0.82 SC. Clear in, heat absorbing out, there's 6 mm, 1/4 inches, 0.36 T solar, and 0.58 SC. The shading coefficients of other commonly used fenestration products are given in this table for summer design condition. On the left side, a properly sized overhang blocks off the sun rays completely in summer. while letting them in through winter. The sun is high in the horizon in summer and low in winter. A properly sized roof overhang or a horizontal projection blocks off the sun rays completely in summer, while letting in most of them in the winter. Such shading structures can reduce the solar heat gain on the south, southeast, and southwest windows in the northern hemisphere considerably. On the right side, draperies reduce heat gain in summer by reflecting back solar radiation and reduce heat loss in winter by forming an airspace before the window. In summer, they reduce heat gain primarily by reflecting back direct solar radiation. The semi-closed airspace formed by the draperies serves as an additional barrier against heat transfer, resulting in lower U factor for the window and thus a lower rate of heat transfer in summer and winter. The solar optical properties of draperies can be measured accurately, or they can be obtained directly from the manufacturers. External shading devices such as overhangs and tinted glazings do not require operation and provide reliable service over a long time without significant degradation during their service life. The primary function of an indoor shading device is to provide thermal comfort for the occupants. An unshaded window glass allows most of the incident solar radiation in, and also dissipates part of the solar energy it absorbs by emitting infrared radiation to the room. The type of climate in an area usually dictates the type of windows to be used in buildings. In cold climates, where the heating load is much larger than the cooling load, the windows should have the highest transmittivity for the entire solar spectrum and high reflectivity or low emissivity for the far infrared radiation emitted by the walls and the furnishing of the room. Radiation heat transfer between a room and its window is proportional to the emissivity of the glass surface, and low E coatings on the inner surface of the windows reduce heat loss in winter and heat gain in summer. Tinted glass and glass coated with reflective films reduce solar heat gain in summer and heat loss in winter. The conductive heat gain or losses can be minimized by using multiple pane windows. Double pane windows are usually called for in climates where the winter design temperature is less than 7 degrees Celsius or 45 degrees Fahrenheit. Double pane windows with tinted or reflective films are commonly used in buildings with large window areas. Clear glass is preferred for showrooms since it affords maximum visibility from outside, but bronze, gray, and green colored glass are preferred in office buildings since they provide considerable privacy while reducing glare. That's all.
So again, we are Group 4 presenting to you solar energy applications. So thank you for listening.